The problem we're trying to solve with this project is the following. Have you ever been to the library on a busy weekday and have not found where to study? Well, our team has created this amazing IoT device from the knowledge gained in various CS classes and ECE courses, mainly Professor Wiglinski's Introduction to Communications and Networks class, ECE2305. First, let's meet the team. Hey, I'm Musa Contreras and I'm a double major in robotics and ECE.
Hey, I'm Anastasia Karapanagu and I'm BME in psychology.
Oh, hi! I'm Phoebus Cavassalis and I'm a double major in ECE and CS.
And we should not forget about our fourth teammate, John. He will appear later in the video. Search and pick a seat. This system consists of one aggregator node and multiple sensor nodes. The sensor nodes gather information every t seconds. This information is about what seats are available or not. First, the aggregator node calls on each individual node and gives them a time slot to transmit their data for the seats they are monitoring. This is called the TDMA protocol. Then, the aggregator node receives this data and the sensor node stops transmitting. After that, the aggregator node calls on the next sensor node and so on. Once it reaches the last sensor node, it compiles all the data and shares it to the web. In this case, we're using the Blink web sharing application. Now, let's see the implementation process and how this Internet of Things network works. For the project, we used an Arduino Nano with a cost of $429, a 433 MHz RF wireless transmitter and receiver modules with a cost of $1.80, an HCSR04 ultrasonic sensor with a cost of $2, and some LEDs and wires that we had lying around. The reasoning behind using an ultrasonic sensor is it operates at a frequency of 40 kHz, which is beyond the human hearing capacity. In addition, it has a range from 2 centimeters to 4 meters, which is perfect for the purposes of our system. This ultrasonic sensor is placed near the cubicle to monitor if it is empty or not. By sending a 10 microsecond pulse, high state, to the print trigger, the module will send out an 8-cycle sonic burst. Then, the equipment will receive this burst and output the time in microseconds by doing a little bit of math. This communication protocol is referred as TTL or transistor-transistor logic, which means that the level will always be logic high or logic low, a square wave. Therefore, we can use this to find a distance from the object, or human in this case, from the ultrasonic sensor. Furthermore, we use the cheap 403 MHz RF wireless transmitter and receiver modules, which work fairly good. Now, John will give us a small lecture on these modules. Take it, John.
According to our research, adding an antenna to the transmitting and receiving modules would enable the signal of our system to be propagated to significantly greater distances, therefore minimizing any attenuation or path loss problems that would normally take place. However, it was brought to our attention that over-amplifying the signal could cause interference with other signals in the area and could even get us in trouble with authorities. Therefore, we carefully designed the antennas to result in a range of approximately 20 meters.
We hooked up the circuit in the following way. First, we connected the Arduino Nano to the board. Then, we connected the receiver module to digital pin 11 and the transmitter module to digital pin 12. Lastly, we connected 3 ultrasonic sensors per Arduino Nano because that was the max that it allowed us. Now that the physical layer is all set, we will take a look at the protocol we used and the code where the transport layer, application layer, and web sharing layers are. First, we use the time division multiple access protocol because it allows us to send various datagrams from multiple sensor nodes through one frequency. This is perfect for our system because it allocates a time slot for every sensor node where it can send its process data to the aggregator node. Then, the aggregator node processes all that data and sends it to the web. Furthermore, the system uses amplitude shift keying, or also known as ASK. This method is used on these modules because it is a very simple method for sending digital data represented as digital 1 or digital 0 through these inexpensive modules. This is done by a simple on or off manipulation to the carrier wave. But now, you may be asking yourself, how do we know where the data is coming from? Well, as we have learned in class, we have implemented a very simple datagram that consists of overhead and data. The overhead, in this case, is the name of the node, and the data attached is either a 0 for a free seat or 1 for an occupied seat. Now, let's take a deeper look into the code to see how this is done. So let's first take a look at the code for the aggregator node. Right here to the right, I have a flowchart that we will be looking at. So here, the main libraries to include are the Radiohead library that uses the ASK amplitude shift keying that we talked about before in the video, and the SPI library. This part right here is the Blink library that uses an authentication code, and this is basically our web layer. Some instructions in our code are basically, we have these two main super important variables. That the first one is to set the max sensor node, so this basically sets how many nodes are in the network of our Internet of Things. So now going into the loop, we have to run the Blink software every time, so it just updates it to the web. And here's where the fun part is, the switch case. So this is our first case. Here we transmit the node number from the aggregator node, so basically all our sensor nodes are listening for this part to be, so they are called. Here we have the name of the sensor node that's being called, so it's a node number. It will change on every iteration of this aggregator node. It will be added, so first one is 0, then 1, 2, 3, 4, 5, 6, 7, 8 until like 9. Then we send it with the Radiohead library, and then we break into the receiving data state. Here in the receiving data case, we check if we have received the message or if we have not received the message. If we have received the message, then it would go into this if statement. It will process the data. This is a helper function that I can show you right now. Okay, so this is a helper function that we have made. It passes in the datagram, basically, that is a string, so it's the message received from the sensor nodes, and then it parses all of them, so it splits them up, and then it saves it to some global variables that we have set right here. Then returns true when all the process is done. After that, it saves the data with a really easy helper function, and then it shows us that it has received it by setting off the LED receiving LED low, and then changing the state to the next node. Then we go to the next node case. In here, we will basically just increment the node number, so in this case the node name. And then after that, we either go back to the transmitting node number case, or we go to the web layer. So basically this if statement right here is saying if we have reached the max sensor nodes, then go back to the first one, so 0, and then change the set to web layer. So we're not updating too fast the web layer part of it. And then here in the case of the web layer, we just print to web. This is basically just using the blink. I'll show you right here. The blink terminal to just print the seat, then the seat number, and if it is a 0, or if it is free, or if it is occupied by a 1. And then after that, it goes back to the first case where you transmit the node, and this iterates through all of the nodes and then back again. Yep. So this is basically the flow chart for that. But the difference also is that our team wanted to transmit that the aggregator node had received the data from the sensor node, but then we realized that it was going to be too complicated and there could be more collisions than we wanted to, so we kept it simple. Now let's go to the sensor node. So here the important variable to notice is the node ID. So this is basically the ID of the node, in this case 1. You can change it to 0, 1, how many sensors you have. No sensor should have the same node ID because that could create a lot of collisions, and because both sensors are going at the same time. And then set the state to listening. That's the first state. So in the listening state, we're basically listening for the aggregator node to call on this sensor. So this is just for printing purposes. Here's the important code. So if it receives a message, it can be like not even its own like name, but it can be any name. Then it says, okay, am I this node that the aggregator node is calling? And if not, then it doesn't do anything. It just keeps iterating through this case. But if it is the sensor that the aggregator node is calling, then it changes the state to transmitting data. So basically, in this case, transmitting data, we're basically using this function, this helper function, to get the distance from each person from each sensor on the sensor node, and then we are parsing it all together to create a datagram. And then here's also a TDMA, basically pretty simple, really simple TDMA, that if count is greater than 1, then state equals listening. So if there's one iteration of this, then it will just change state to listening. That is basically what time division is. Function that I showed you above there puts it all together into this simple datagram that then in the sensor node, in the aggregator node, we separate and put it through its own channels.
The main problem encountered by our team was that all our receiver modules got damaged somehow. We started with 5, and by the end, we only had 3 of them working, kind of. We suspected that the main problem was that they were very sensitive, and we may have wired them incorrectly, which may have burnt them. We would like to thank Professor Wiglinski and the ECE2305 class for teaching us how to make this system. We hope you have liked this video. Also, do subscribe. We're a fast growing channel.